Now let's get started. Hello everyone, welcome to this today's webinar on the quality control and improvements tool in Origin Lab. My name is Yiming Chen and I'm from Origin Lab technical support team. And in this webinar, I'm gonna focus on three topics: the statistics process control and the measurement system analysis and the design of experiments. During this webinar, if you have any questions, you can put it in the Q&A window or the chat window, and my colleague Chao Yuan will help to answer them. Okay. And also, the recordings of this webinar will be posted on our website early next week, and you can come back to review. Okay. Let's get started. So first of all, if you go to our webpage, www.originlab.com, and we have a page with this quality improvement statistics. And if you go down, you can also find the page link in the quality improvement. Okay. And yeah, it lists all the tools that are supported in Origin in this area. Okay. Statistic process control, SPC, multiple different types of control charts, process overview, capability analysis, the nice report sheet, and you can quickly check here, and different distribution identification, measurement system analysis, okay, gauge studies, tolerance interview, and also design of experiment tool. We also support it. And other than these, we also have different types of statistical charts for you to explore the process, okay, and other tools, okay. And I will cover most of the tool in this page today, okay. Another thing I want to mention is starting from Origin 2025, we add a menu from the statistics quality improvement, and you can get a quick access to these tools. Okay, all of these tools are available as a form of apps. If you use the apps in Origin, you know that you can come to the apps panel, okay, and just add apps. And you see here, I have added a tab to just organize all of my statistics process control tools here. Okay. Okay, now let's get started. The first thing I want to cover is the statistical process control. Okay, so statistical process control, SPC, is a tool to answer questions related to the stability and the performance of process in industry. So you may want to know whether the production process is stable and consistent over time, and is there any the special cause of the variation, and whether there is some outliers during the process, and people also want to know the capability of the process. Okay, so in Origin, we introduced this a tool called a Statistics Process Control. It's available as a form of the app. Please download and give it a try. Um, I will talk about the quality control charts first. Okay. Before we going into the control charts, there are many different types of uh, statistical graphs that helps user to understand the process better. Okay, for example, we have this probability plot. It helps you to test whether the process, the measurements is normally distributed. Pareto charts, yes, we support that, and different types of variability charts. Okay, so you can check the variation of the measurements of different factors. Okay, and then also different types of control charts. I will cover that in detail later. All these plots are available if you go to the plot menu and go all the way down to no, that's in the middle, the statistical category. And at the bottom is a row of the plots that are related to the quality control. Okay. You can also go to our help menu and the learning center. if you just search for yeah, I think there's a category. So you go to the quality control category, and there are also different graph types templates here that you can choose to learn how to make each graph. Okay. Yeah, let's go to the numerical control charts. Okay, so let's see this data set. I have this one column of the measurements data. So here it says it's the quality engineer wants to evaluate the pipe production process, and he collects data for the height of a pipe for 150 samples. Okay, so these are like individual measurements that they are not grouped, and the engineer wants to know whether the process of production is consistent over time. Okay, so we can use the individual and the moving range control chart. So yeah, as I said, it's an app for the statistical process control. Let me just open the app. There are multiple tabs here. Control charts is the last one. Okay. For the for all the apps in Origin, if you want to check the help documentation, yeah, for example, here you can just click the question mark, and it will give you the document of the tutorial, and as well as the algorithm for each tool. Okay. Okay. Let's start with the control charts for individual measurements. Yeah, so let me start the IMR. Okay, so in Origin, usually the tools, if you launch a tool, it starts a dialog like this. You can see on the top is a dialog theme, so which means you can save the settings in the dialog as a theme file. So basically, you click a triangle and save that as a theme file, which that you can load in the future. Okay. So here I set the measurement data, which is column A. Okay. Then there's other tabs that ask you if you want to do transformation. So if the data itself is not normally distributed, you may want to do a Box-Cox transformation or Yale-Johnson transformation, which are two methods are supported in Origin. Parameters, if you have some historical mean and standard deviation value you want to put here. Okay. And under the estimate tab, it tells you how you want to calculate the standard deviation. Use the average moving range or use the approved standard deviation, things like that. Okay. Yeah, one thing I want to mention is the tests. So uh, we want to check whether there's a certain pattern in the control chart, and this different types of tests help you to identify those patterns. Okay, for now, I will just use a specified test. I'll just use check this one. Okay. Okay, let's click OK. So in Origin, the control charts, first of all, it shows the individual measurements as a function of time, and it displays the outliers. Okay, so there's a one outliers on the individual measurements. If you hover your mouse to the point, you can tell which the row index of the point, and also which test it failed. So it failed test one. Okay, and you can read the which test it is. Go to the right-hand side, the text part, and if you check the moving range plot, you see like 2 points are outside of the upper confidence level. Okay. In Origin, if you want to check a section or a part of the graph, you can, there are multiple ways. You can click the axis just to move the red dot to zoom in. Okay, you can just check the local of the chart. If I just rescale, and you can also use the scale in button. Okay. Um, Also, in Origin, if you want to make changes to the settings in the tool, you can click the green lock. Okay, change parameters. So for example, this time I want to uh, check whether there are other patterns in the control chart. So yeah, I can just say I want to perform all tests. Okay. So you see the control charts gets updated with more tests. Okay. So it's like a 5 is like out of 3 points more than 2 standard deviation from center line. So you can from here you can test like if there are clustering pattern, there's oscillating patterns, etc. Okay. Another option in for the control chart is that you can add stages. So assume the measurements are taken from 3 different stages, and you want to check the statistics for each stage. You can just specify the stage and click OK. Yeah, then um, the control chart will do the outlier or the pattern detection for individual stages. Okay. This is the control chart for the individual measurements. Let's check another data set. So here, let's read the introduction. It's the quality control department drew 4 nuts from the finished products of 2 machines per day for 20 days. Okay, so this is measurements uh, which is grouped by the time. So each day there are 4 measurements, and I have 2 sets of data. Okay, then let's do control charts, which the data has the subgroups. Let me just highlight the 2 columns and go to the tool. And this time I will just choose the variable charts for subgroups. Let's do mean and range control charts. Let's select the X bar R. Here again, so just so you know that this control charts tool supports multiple inputs. So this time I have 2 columns selected. And for the subgroup size, you can specify a constant. Say each group has 5 uh, samples, or you can use a column to specify the grouping. So here I will use column A. So it's grouped by the day. And the rest of the settings are similar to the individual control charts. Yeah, let's again just perform all tests. Okay. If I click OK, it will generate 2 control charts for each process. And if you look closer, it plots out the subgroup mean, okay, as a function of the date, and also the range of each subgroup as a time of the date. Okay. Let's go to next example of the attributes control charts. So sometimes the measurements is not numeric. For example, here I have this data set that this is uh, a survey. So people, the manager sends out the survey and gets response, number of responses in column A, and the number of responses corresponding to unsatisfied users is in column B. And people wants to whether the proportion of the unsatisfied users is consistent over time. Um, so in this case, we know that this data sets follow a binomial distribution. So we can use the attribute control charts to see whether the process is consistent. So again, let's go to the attributes control chart. Okay. If you know the process, the data follows a binomial distribution, you can use a P chart or Lenny P. So you can use the P chart diagnostic, this tool to identify which control charts to use. So this case, I will just use the Lenny piece. So for the measurements data, I choose the number of the unsatisfied users. And for the group, I will use the total survey responses. Okay. Yeah, click OK. Yeah, because the number of surveys sent out, the response received are different for each day. So you can see the limit, the confidence limit level is also changing with time, and all the data points are within the limit. So which means the process is consistent. Okay. Um, if we check another data set here, I have a data set which follow a Poisson distribution. So in this case, I have the engineer wants to evaluate uh, the flaws or blemishes on the film, and he cut a certain area of the film, which is saved in column A, and he counts the number of blemishes of each film on the column B, and he wants to check whether the number of blemishes for each, for example, for each centimeters are consistent over time. Okay, he can use this control charts, which according to the Poisson distribution. Here, so in this case, it's we are gonna use the U chart. Okay. Let's just select the number of blemishes in column B and the subgroup size, which is the area, and quickly check the results. Okay. So here's one data point, which is the outside the confidence limit. Okay. Okay, now let's move to the next tolerance interval. So again, we have seen this data set. It's the measurement of the heights, and people wants to know whether in the production in the future will fall in a certain range with a certain confidence level. So in that case, we will use this tolerance intervals, this app, which is also supported in Origin. Yeah, I will quickly show you. Um, I don't know, maybe this data set follows the normal distribution, but this tool also helps to identify uh, the oh, so okay, something is not right. Mm, let me quickly install the. Okay, okay, so let's quickly check. In this case, the input data is the column A, and people wants to know the range of the 99% population will fall in this population, and with a confidence level of 90% or 95%. Okay. Okay, so here we can quickly tell that the lower and the uh, upper bounds for the new production that uh, will 99% of the new production will fall in this range with 95% of confidence. Okay, if we compare that with the specification, okay, which is smaller than that, which is good. So uh, people know that the reproduction of this product is reliable within that bound. Okay, let's go to next process overview. Um, a quality engineer, okay, this time they collect the data grouped by the time. Okay, they run um, eight measurements for each timestamp, and he wants to know whether the production will or meets the requirement of the specification that to be to 15 plus minus 20 milligram. Okay. So before we do the capability analysis, people want to know whether the process itself is consistent and whether it is the process is normally distributed. Okay. So in that case, we have this process overview. Okay, let's again go to the statistical process control process overview. Okay, let's use the normal process overview first. So measurement data is column B, and the group information is in column A. Um, to use this tool, you need to specify the specifications. So the lower spec is 195, and the upper is 135, and the target is 215. Okay. Yeah, again, you can turn on the um, all the tests and click OK. Let's check the result. Okay. Um, First of all, if we look at the X bar chart, there's one outlier. Maybe the process itself is not very consistent. Okay, but if we check the points, they are almost randomly distributed um, to the mean line. So we can tell this is almost a random process. And if we check the normal probability plot, the p-value is 0.017 below 0.05, which means it's at 0.05 level, it's not normally distributed. Okay. And if we check the capability histogram, we can tell that let me make it larger. The two uh, distribution curves are not aligning very well. So which gives us some indication that other than the within group variation, there are also between group variations that we need to add to this analysis. Okay, and if we check the capability plot, the uh, the overall variation is smaller than the specification a little bit. Okay. And you can also read these statistics in the table here. Okay. If we want to add the between group variations into the model, we need to use this between within process overview. Okay. I check that. Again, I quickly choose the group and the measurements and the limits. To 195. Okay, now if we consider the between group variation, then the overall distribution curve and the between within normal distribution curve are almost aligning. So which tells us is the between group variation in the process. Okay. We can also confirm that from the capability, the index table here. Okay. Okay, so this is the process preview, so which is the step before we do a full capability analysis. Okay, let's now go to the capability analysis using the same data set. Okay, yeah, in Origin, the capability analysis is under the tab here, and yeah, we know that we should use the between within capability analysis. Okay, let's just choose this one. Measurement is column B, and the group is column A. And again, 190, 195 to 35 to 15. Okay. Yeah, so the other settings are similar to control charts. You can put the historical measurements here, and you can, yeah, specify the K value for the capability calculation. Okay. Yeah, we can quickly read the capability index. So the PP value is almost 1, which is below the reference value of like 133. So it's the process itself is not very capable. There's room for the improvements. Um, but we can say that the measurements are almost centered at the target. Okay, because the PPL and PPU value are very close, and okay, and we also can also check the CP value, which is between within capability. Okay, and also the descriptive statistics, we can read that from the process data here. And also for the performance table, we can read yeah, we can use control to zoom in. Yeah, we can tell the percentage of the process of the of per million is within this the confidence interval. Okay. Okay, this is the capability analysis. Let's go to the measurement system analysis. Engineer, other than want to understand the stability and the capability of a process, they also want to check whether the measurements itself is reliable. So the the measurement system analysis is the tool to assess the accuracy, precision, and the reliability of a measurement system. So in this case, the measurement system can be the gauges to measure measure the product, or it can be the operators that to conduct the measurement. So the MSA tool can help to identify and quantify sources of variations in the measurement system, and also provide and also answer the question like whether the measurement system provides consistent result across the range of the measurements. Okay, we will check a couple for the gauge study tools here. The first one is a type 1 gauge study. So what the type 1 gauge study doing is that we have a sample of of a no size, for example, and the one operator just measures this object multiple times, and then we can use the data to test whether the gauge itself is reliable, whether there is a bias in the measurements. Okay, so here I have this measurements of certain objects. One operator measures it like 50 times, and we know that this is a standard object with a height of 5 feet. Okay, then let's use a type 1 gauge study to test this gauge. Let's just choose this gauge study app. Okay, and I choose type 1. Here for the measurement data, I will choose column A. And we know that this object has a reference size of 5. Okay, and we need also to specify a tolerance value. So I put a 0.1 here. Okay, yeah, just click OK. So in this round chart, uh, we can tell that the measurements are all within the tolerance level. Okay, and if we just check the statistics, the 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 standard deviation of the measurements is here, and the mean value and the reference value is 5. And in the second column, it tests whether there is a bias of this gauge. So we can just simply read the result, the conclusion. That can't reject bias equals 0. So which is good. And we also can measure the capability of the gauge. So the CG value is again, it's the almost one below the reference value 1.33, which means the gauge can still be improved. But we can tell that the variation is like 20% um, to the entire variation, and the repeatability and the bias total is only just 21. So the bias can be effect of the bias can be neglected in this case. Okay, let's check another example, the gauge linear bias analysis. So for every measurement system of the gauge, it has its own measuring limit. So people want to know whether the measurements is consistent across all the entire range of the measurement of the gauge. So here the engineer just have 7 parts. They sort of like indicative of the expected range of the measurements. So it's from two. We know the reference value of the object is from 2 to 14, and the column C is the measurements. Okay, then we can use the linear bias analysis tool. It's still under the gauge study, gauge linear bias. So here we have 7 parts. So I just choose the parts number is column A. The reference value is column B, and the measurements value is column C. Okay. Yeah, people may need to specify process variation if you know the value. Okay. Yeah, so in this graph, it just basically plot the bias of the measurements as a function of the reference value. Okay, so we can quickly tell that there's the linear effect here. So when the bias gets increased when uh, the size um, is close to the limit. Okay, so you can read from the gauge linearity table that both the interception and the slope is significant. The p-value is way below point oh 0.05, and the variation due to the linearity is like 11% of the whole variation. Okay, because of that, we can only tell the variation for individual part. So we can check the gauge bias here. So at the measurement of 8, the p-value is above 0.05, which means there's no bias. But when it's reached to the boundaries, like uh, reach to the limits 2 or 14, the bias is significant. Okay. Um, and in this graph, we can also check the percentage of the variation due to the linearity and due to the bias. Okay. So this is gauge linearity and bias uh, test. cross-gauge um, cross-gauge study. So we have the previous 2 tools just to measure the uncertainty of a gauge, but we can use this cross-gauge study to measure the variation or uncertainty of the measurements according to different operators. So uh, we have, if I just open this tool again, we have the crossed gauge study, nested gauge study, and an expanded gauge study. So there are different setup of the experiment. Okay, so for the cross gauge study, it just um, so for example, here I have 10 parts, and there are 3 operators. Each operator will measure these 10 parts individually with 3 times. Okay, then this is the column C is the measurement. Okay. Um, then I want to user may want to know whether there is the variation due to different operators, and for each operators where there's a variations between the different trials. Okay, so let's go to the gauge study and go to cross gauge study. Okay, so again, the part number is in column A, and the operators are in column B, and the column C is measurement data. Okay, so let's just click OK. Um, so we can check the couple of the plots here. So first is the sample range. We can see for three different operators, the measure the sample range are quite different. So for the operator C, it has a lot of outliers. So the operator C, the measurements done by operator C is not very consistent. And for the sample mean for three operators, they are way beyond the confidence level, which means the variation are not from the operators, are mainly from the different parts. Okay, and we can also check uh, the the parts, the measurements of each part. Okay, so what's more important is this result table. Okay, that basically it's running a ANOVA analysis with the responses measurements and the two factors, the part and the operators. So here we can see both the part and the operator has a significant effect. So the p-value is low, but the interaction of the part and the operator, the effect is small. Okay, so when we do the gauge calculation, the interaction term is removed. Okay, in the variance components table, we can quickly read the repeatability um, value and the reducibility value. So reproducibility is from the effects of the operator. Okay, it just it's very small compared to um, the 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 gauge um, variance. Okay, so the part-to-part variation is the most, which is consume 92%. Okay. Okay, now let's look another tool called attribute agreement analysis. So in previous example, we are doing the measurements itself is a numeric. So what if the measurements is a attribute or categorical variable? So here I have this table which I have like five appraisers, and they just evaluate 40 samples, and for each sample they evaluate twice. Okay, they give it a rating from -2 to 2. So the measurements are in column E, which are categorical variables. Okay, and oh sorry, the measurements is in column D. Okay, the standard rating values are in column E. So uh, when after doing this test, people may answer the question like whether there's a consistency of each operator's rating within trials, and also the correctness of each operator's ratings compared to the standards. Okay, so we have this um, attribute agreement analysis. So when I start using there are two types of organizations of data that we support. So in this case, all the ratings are all in one column. So we say it's a single column um, the arrangement of the data. So for the attribute rating data, we choose column D. And for the sample index, it's column A, and the appraiser, column B, and the reference rating values is all in column E. Okay. Yeah, let's just click OK. Yeah, it creates a lot of statistics. Okay, so um, yeah, so in Origin, for each table, you can click this note to collapse or expand the result. Okay, we can just quickly check the agreement graph. So in the within appraiser graph, we can quickly tell the appraiser C, okay, he has the most consistency. So uh, between the trials. So, um, and also it has the lowest variation or uncertainty for appraiser C. And if we check the appraiser versus standard, again, the appraiser C and appraiser E has the best correct the rating. Okay, and you can also read the other statistics. So from the statistics here. Okay. Okay, let's go to the design of experiment. So design of experiment is a systematic approach to optimize the process, improve product quality, and understand the factors that influence a system. So usually a DOE process contains 4 steps. The planning step, people may want to know the number of rounds of experiment in order to achieve a certain goal of the testing power, and also to reduce the resources that needs for the design. And after they determine the sample size or the number of rounds, and they can design the table, the table, then do the measurements to fill out the table, then use the measure data to do the modeling of this design so that they know the effect of each factors. Um, Afterwards, they can also do optimizations to find the most the optimal combination of the parameters to reach certain goals. Okay. Um, so let's go to the power in the sample size. Uh, Again, in Origin, the design of experiment tool is available as as an app. Okay. If I just click that, yeah, we can quickly take a look at the help menu. Yeah, it lists um, it has a very explicit introduction to each design, okay, and what the each the settings in the dialog means. Okay, you can quickly check here. Let's start with the power and the sample size. So this tool supports 3 factorial type of design: 2-level factorial, Plackett, Berman factorial design. If you want to do the factor screening, you can use the second one, and the general full factorial design. So you can have more than 2 levels for each factor. So let's just use a 2-level factorial design. Assume that we have 3 factors. Yeah, you can specify a number of factors in the model. And yeah, you can, if you want to include all the combination of the factor levels, you just choose the full factorial design. And number of blocks, let's choose 2. Yeah, then we can go to the settings. So in this table, you can specify which parameter you want to calculate. So let's say I want to calculate the power of this design based on other parameters in the setting. Okay, so how many replicates for the measurements? Yeah, I can specify multiple values. Okay, I want to know the power at replicates 2, 3, and 4. And you need to specify the effect values. So effect value is like the rough guess of the difference between the levels. Okay. And the power is what we want to calculate. So it's grayed out. And number of center points, yeah, let's say 0. And a standard deviation, so which is the variation of the measurements. Okay, so basically this value is supposed to be smaller than the effects in order to have a better result. Okay. Okay, just click OK. It, yeah, basically it calculates the power for different replicates. Okay, and also it gives the total runs of the experiment. So you can use these informations for the design building. Okay. Now let's go to the design experiment. Okay, so this the second icon here. Um, so now we also support the definitive screening design. Okay, so the purpose of this design is to screening out the the factors affect the response. So this is the most useful when you have many factors and the interaction between the factors are not that important. So it's a quick way to for the factor screening. And we have the factorial design and the response surface design. Okay, so let's just use the factorial design. Again, we support three factorial design, and you can click the display available design button. You can check the resolution of each design based on the number of runs, okay, and number of factors as well. Okay, so here you can specify the number of factors. Yeah, this is some pre-inputted values. So I have three factors: temperature, density, and the reagent. And two of them are numeric, and one is categorical. Then you just type in the low and the high value. Okay, and there are two reagents, type A and type B. Okay, just so you know that the settings in the dialog can be saved. Okay, so you can save it in as a XML file, and you can load it for the future use. And for the settings, let's say I want to do a full factorial design. So yeah, it may be expensive, okay, because all the combination of levels are considered. And number of blocks, yeah, let's just say two. Number of replicates, two as well. Yeah, when we do the power and the sample size calculation, we know that this design will generate how many runs and the power of the design is. Okay. So the rest settings are just keep it as it is and click OK. So Origin will generate this design table. Um, yeah, you can tell there's 16 rounds of the experiment. The 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 factor levels. Then you can just fill out this table with your measurements. Okay, then run the modeling. And also, just to know, there are two sheets generated. So in the first sheet, it contains the summary of this design. Okay, everything you want to know about this design is listed here. Okay, then I can use this design table to run experiment, then do a modeling. So assume that I have this, I fill this table with the pH value as a response. Okay, then I will use the analyze design tool for the modeling. Okay. So in the dialog, I specify the response to be pH value. And by default, only the main factors are listed: temperature, density, and reagent. So we can include the interaction terms by clicking this plus button. So if I say set the order to 2, then all the interaction terms in the model are included. Then go to the settings, confidence level 0.05, that's fine. Quantities, you can click the drop down to see to add or remove the coefficient the parameters in the coefficient table, and also the statistics of the fitting. And you can use this model to do the prediction. So if you want to find the response from the predictors, you can just check this box. And if you go to the plots, different kinds of plots to help you to understand the model. Yeah, let's just check all of them. Okay. So for the cube plot, I would just specify all three factors. And for the contour and surface plot, you need to specify the XY value, XY axis value, and also specify one reagent. Okay, and click OK. Okay, so in the table, let's just move down to the effect plot. So it helps us to know which factors is most significant in the model. So here the reagent type B and also the temperature. And all the interaction terms are not significant. Also the density is also not significant. Okay. Yeah, we can tell from the ANOVA table that just by reading the p-values. Okay. So once you think that you want to modify the model, for example, you want to remove the interaction terms in the design, you can go back and click the green lock and change parameters. So again, go to the model tab. Yeah, just set it to first order. Okay. And click OK to update the report sheet. Okay, so right now the interaction terms are excluded from the model. Okay. Then you can see other plots like, for example, the cubic plot. You know, at different uh, level factor combinations, you what the response is. Okay. Yeah, we can quickly tell that the maximum response happens at temperature 50, density 20, and the reagent type B. Okay. And from the contour and also the surface plot, you can tell that the temperature effect is significant, but the density effect is not. Okay. Okay, so once we have we have built up the model, and we can use this to do optimization. Okay, if I just click that button. So let's say I want to minimize the pH value, minimize the response, and we want to see at which combination of the factor levels gives us the minimum value. Okay, you can manually specify a lower and upper limit, or you just click the button. So Origin uses some algorithm to specify the bounds, and you can apply constraints to each factor if you want. And also, if you set initial value, it will help you the optimization to converge. Yeah, and then click OK. Okay, so in the solution table here, it tells us that at temperature 80 and the density 30 and the reagent type A, we reached the minimum value of the response, so which is 6.3. Okay, and we can also open up this interactive graph to quickly check how each factor will affect the response, and you can also move this horizontal bar to check the response at different factor levels. Oh, okay. Yeah, and then click reset to go back to origin. Okay. Yeah, so this pretty much the DOE app. Yeah, just so you know that for the most of the tool, if you let's say the design experiment, if I right click and say I want to open the app tutorial page, yeah, it gives you a step-by-step tutorial to run each app. Okay. And also each app contains sample data. So it shows sample folder, and you can use the sample data to try the tutorial. Okay. Okay, so I think that's pretty much I want to cover in today's webinar. And thank you for your time and patience, and have a good rest of your day.